Okay, welcome back everyone. Let's get started. So we are in the fifth lecture today, and today we're going to switch over to classification. And before we switch over, let's do a quick recap of what we've covered. We covered prerequisites, and we started with supervised learning. And supervised learning is basically learning a mapping from X to Y. And we started with regression and looked at the very first regression algorithm, linear regression, where we are trying to learn a mapping from some example X, which lives in a d-dimensional space, to an output Y, which is a real value. And we assumed, or we limited ourselves to hypotheses or models which belong to this family of the form theta transpose X, where theta is some parameter that identifies the specific member of our hypothesis family. And we wanted, or the desired outcome is x theta, or here X is a design matrix and Y is the vector of all outputs. We want X theta to be as close as possible to Y. But in general, this will never hold true. X theta will almost surely never be exactly equal to Y. And the method that we fall back to is to define a cost function, which is the difference between X theta and Y, X theta minus Y, and that is going to be a vector, and you take the squared norm of it. And the squared norm is basically exactly equal to the sum of the squares of the individual terms, or the sum of the errors of each example, right? And we want to minimize this sum of squared errors by choosing an appropriate theta. Okay? And we saw two different kinds of solutions for that, a numerical solution and a closed form solution. So in numerical solutions, again, we saw two different methods, gradient descent and stochastic gradient descent. The key difference between the two is with gradient descent, we consider all examples for every step. So these are iterative algorithms where at each step we start with a random initialization of theta, and at each step, time step, we make some change to theta updated by some amount. And in gradient descent, for each update we consider all the examples, and for stochastic gradient descent we consider one example at a time. And the way we perform the update is that for the next time step, the theta for the next time step is going to be theta of the current time step minus alpha, which is some step size, times the gradient of the loss, and this happens to be the gradient for the squared loss. I probably forgot a half over here for this to be the gradient. And another way of writing the same thing is, in this notation we have different variables for theta t and theta t plus 1, but if you're implementing this in a computer program, you would have some variable for the parameters, and you keep updating it over and over. So when we use the notation of colon equal to, it means you're performing an in-place update of the variable, which makes more sense if you think about a computer algorithm, whereas this makes more sense as a mathematical expression. So you update theta in place by the current theta plus alpha times the negative gradient. Right? These two are exactly the same. I changed the minus to a plus and therefore swapped the order. And theta transpose X is basically the hypothesis. This is an important equation to kind of pin it in your memory. We're going to see this pattern over and over again. And then there is the other solution, which is the closed form solution. It exists for linear regression, but it may not exist for different kinds of models or algorithms, in which case you'd use gradient descent or stochastic gradient descent. But for the linear regression alone, you can start with the cost function, do some matrix calculus, take the derivative, set it equal to 0, and you end up with the normal equations, which you can invert to get the closed form update for calculating theta. This is not an iterative algorithm. You calculate this and bam, you have the final solution. You don't have to iterate over and over. Whereas with numerical solutions, you want to iterate over this over and over until you hit some kind of a convergence condition, which means your theta has stopped changing a lot, or your cost has stopped reducing, So there are different kinds of convergence conditions we discussed in the last class, but this would be iterated until you hit a convergence condition. But this is just a one-step algorithm where you calculate the final solutions and you're done. Okay. And we also looked at a couple of interpretations of linear regression. The first is if we assume a Gaussian noise for each example, which has mean 0 and some constant variance sigma square, which actually does not matter for our calculation because we assume it to be a constant. It could be a big variance, small variance, it doesn't matter. As long as it's a constant variance for all examples, we are good. And we assume that y is the observed y is some true y. This is some kind of a true y plus some noise. So right, you can kind of think of this as the signal, and this is the noise, right? And you are making a noisy observation, right? And the goal of linear regression is to, given x's and y's, we don't know what the individual noise terms are. Given x and y, we want to recover theta, right? We want to kind of weed out all the noise and extract the signal. That's the general intuition. And with this assumption, we get a likelihood expression, p of y given x, or the density for y given x and theta to be this Gaussian distribution. And when we take the log likelihood, we saw that even though the Gaussian distribution has all these terms, when you take the log, kind of all of these are constants. The log and the exponent cancel, and this is constant for all examples, and this is just another constant. So the log likelihood essentially boils down to just the squared error between the prediction and the observed noise. And we perform maximum likelihood estimation. We've seen maximum likelihood a couple of times so far. Maximum likelihood is basically take define the likelihood across all the examples. And because of the independence assumption, you can, the joint likelihood is just going to be the product of this term across all examples, and then take the gradient of the log likelihood with respect to theta, set it equal to 0, or you can solve it with gradient descent, right? So and what we saw was that performing maximum likelihood estimation was exactly the same as minimizing the squared error loss, right? There's a negative term here. So maximizing the likelihood is the same as minimizing the squared error loss if you assume your noise to be Gaussian, right? In general, if you are defining your objective to be the maximum likelihood objective, right, it has a one-to-one correspondence with having a loss where the loss is equal to the negative log likelihood. Right? Take the log likelihood, flip the sign, and that is your loss function. And in this case, you take the likelihood, take the log, flip the sign, you just get the squared error. And this holds true for any probabilistic model, not just one that assumes Gaussian noise. It could be any probabilistic model whatsoever. You define the likelihood, take the log of it, flip the sign, that's a loss function. Right? Now we saw yet another interpretation, the projection interpretation, where we want x theta to be equal to y, but that's never the case because y lives in a higher dimensional space compared to theta, right? And theta will map to some subspace in this y space, which goes through the origin, which is also the column space of x, and the observed y will almost surely never live exactly on the subspace because we are adding some noise. If the noise was 0, then you would expect your y to be some linear combination of x's, but because there is some noise, your y will be outside the subspace, right? So instead, what we want to do is project this y onto the subspace. Let's call it y hat, the projected point, right? And once you project it, you can actually solve x theta exactly equal to y because now it's projected onto the column space, right? And the way you project it is to take y and multiply it by the projection matrix, right? And this whole term will be y hat, the projected point. And now x theta will will actually be exactly equal to this projected point, and because because they're exactly the same, you can cancel x, and you get theta equals x transpose x inverse x transpose y, which was the normal equation what we saw about, right? So that's what we covered. Any questions before we move on to classification? Yes, question. So in this case, how do we know X matrix is invertible? For now, we will just assume X matrix is invertible, and we'll come up with remedies for later in the course when it's not. So for now, let's assume X matrix is invertible. Yes, question? So the question is, if the observations are not independent, does this theory all hold? If the observations are not independent, none of this theory holds, right? All this theory is making an independent assumption, IID assumption, right? Only because of which you can multiply them together, take the log, decompose it into separate sums. If they are not independent, it becomes much more complex to analyze. However, in practice, even if examples are related, they tend to work well, except the intuition to have is that if your examples are not independent and somewhat correlated, your one intuition to have is that your effective data set sizes become smaller. Think about it. If you have a data set of 100 examples where all the 100 examples are the exact copies of each other, right? Even though you have 100 examples, they're not independent. They're all exactly the same, and your effective data size is just 1. Right? So similarly, if your examples are not independent, your effective data size is kind of reduced, and yes, the theory also does not hold. In practice, think of it as a smaller data set. It is much harder, and most of the theories kind of assume you have independent observations. However, when we go later in the course, for example, in reinforcement learning, there actually, across time step, there is clearly, there is dependence. At each time step, supposing you're playing a game of chess, what you do in the next move depends a lot on what you did in the previous move. They're actually not, and in those cases, yes, we kind of give up the IID assumption, and you get, different kinds of theories there. Yes, question? I'm sorry? So the question is, are there cases where you cannot use numerical examples? So generally, numerical solutions always exist. The closed form solutions may or may not exist. That's generally the case. All right, let's move on. So today, the plan for today is we're going to cover so today we're going to cover the perceptron algorithm, and this corresponds to section 5 in the note, section 6 in the notes, and then we will cover logistic regression, this is section 5, and Newton's method, that's section 7. And time permitting, we will try to do a review of some ideas from functional analysis, basically as a way to kind of prepare ourselves for some of the future topics. There is also one section in the notes that is locally weighted regression. That's section 4. Yeah, we might revisit this later, but for now we're going to just keep moving. Right, yeah, so that's the plan for today. And we'll start with the perceptron algorithm. Okay. So the perceptron algorithm is a very simple classification algorithm where you're given examples in, let's RD, and the correct answer or the label or the target is either 0 or 1 for each example, right? So right, this algorithm we study it mostly because of historical interest and also because it's very easy to analyze and to build some good intuitions, right? In practice, I don't know anybody who uses Perceptron algorithm in practice, but it's as I said, it's a very simple algorithm to kind of build intuitions of how classifying many classification algorithms work, right? And in the Perceptron algorithm, the hypothesis h theta of x, right, equal to g of theta transpose x, where g of say some variable z is equal to 1 if z is greater than 0 and it is 0 if z is less than 0. Right? So g is some function, think of it like this. If this is z, this is 0, g looks like this. G takes the value 0 until if the input is less than or equal to 0, and it is 1, if yeah. So and you can actually define it as less than or equal to or greater than or equal to. It doesn't matter. So let's see how it's in the notes. I think in the notes it is greater than equal to. Anyways, it doesn't matter. Let's assume it is greater than or equal to, which means at 0 it is actually 1 and right. So what's happening here? The hypothesis for the Perceptron algorithm has some parameter theta, right? And given a vector input vector x, we do theta transpose x, just like in the case of linear regression, but the output is then, so theta transpose x can take any value, any real value between minus infinity and plus infinity, right? It's just you take two vectors and take the dot product. It can be any value whatsoever. Now we take this real valued number and map it to a value, map it to either 0 or 1. Right? If theta transpose x is less than 0, we map it to 0. If it is greater than or equal to 0, we map it to 1. Right? And with this hypothesis, the algorithm looks something like this. Right? So the Perceptron algorithm is also called a streaming algorithm, which means it is designed to work in a setting where you're encountering examples one after another. You don't have access to all the examples up front. You're just given one example at a time, and you need to update your model and then wait for the next example and then update your model and then wait for the next example and so on. And the algorithm for training the Perceptron looks something like this. So so set your theta to be some initialization. So generally it is just the 0 vector, that works totally fine. And for I in 1, 2, and so on, just a stream of examples that are coming at you. You perform theta equals theta plus alpha times yi minus h theta of xi times xi. Okay. What's happening here? So first we see that the update rule for the Perceptron looks very similar to the update rule of linear regression, right? But they're not actually the same. What's different between the two? Right? H theta of x is different. Right? They look kind of superficially similar, where given the hypothesized value or the predicted value and the actual value, the update rules look very similar, but the hypotheses are actually different. Right? In linear regression, your hypothesis was just theta transpose x. Here it is g of theta transpose x. Right? And there is theory to prove that if your data set is actually linearly separable, then this algorithm will find that separation point. Your hypothesis will be able to classify all the points. It's not entirely clear how this, just looking at this form, it may not be entirely clear how this works, or why it would even work, right? For this, let's try to visualize this. Okay? So let's assume this to be x1 through xd. Again, in all these examples, I'm assuming your x to include the intercept term. Right? So assume it to be d plus 1, or in general it is fine to assume x in d, where d just includes the intercept term and your true data was d minus 1 dimension. Right? We don't stress about that too much. So assume the intercept term is included here, and let's assume your theta vector has some current value. So let's let me use a different color. Let's assume your theta vector to be here. So let's call this theta of t. Right? Your theta vector is currently here. Now, it's obvious looking at this formulation that what really matters is for a given new value of x, whether theta transpose x is greater than 0 or less than 0. Right? The actual value, actually doesn't matter. What really matters is whether it's just greater than or equal to 0 or less than 0, because it just gets mapped to 1 and 0, no matter how larger than 0 it was, or how little bigger than 0 it was. Similarly, if theta transpose x is here or here, it still gets mapped to 0. Right? So what really matters is theta transpose x greater than 0 or less than 0, which means theta transpose x equal to 0 kind of forms a hyperplane that is meant to separate your data points. You want all the points that have y equal to 1 to satisfy the requirement that theta transpose x is bigger than 0 for them, and less than 0 for those that have y equal to 0. Now, if theta is this vector, theta transpose x is the hyperplane, that is this hyperplane corresponds to theta transpose x equal to 0. Right? And because theta is oriented this way, all points on this side satisfy theta transpose x greater than 0, and all x's on the other side satisfy theta transpose x is less than 0. Is this clear? Is this the idea here is that any x that lies on this line is perpendicular to theta, so theta transpose x will be equal to 0. Right? And if you have an x over here, the inner product between them is it's basically less than 90 degrees, so theta transpose x will be positive. If you have an x over here, the angle between theta and x is more than 90, so theta transpose x will be negative. Right? And the line that's exactly perpendicular to theta is like the decision boundary. Is this clear? Okay, great. Now, another intuition that we want to have is, let's assume you have two vectors a and b. Right? Let's assume this is some vector a, right? And let's say this is some vector b, right? And a transpose b equals some value. Right? In this case, suppose a transpose b is some value less than 0, right? And we desire, let's assume this was our theta and this was some x, and let's say this was an x whose y label was +1. Right? We want theta transpose x to be positive. Right? Now, however, theta transpose x is a negative number because it is greater than 90 degrees, and if the desired value of a transpose b or a dot b is bigger than the current value of A dot B, is there a way in which we can modify one of the two vectors to make the desired value larger? How do we make theta transpose A dot B achieve a bigger value is basically the question. So one simple answer for that is take the vector A, right? In this case, think of A as your theta vector, and you have a vector x. What we can do is take a small amount of x and add it to A, which means at the end of A, let's call this alpha times x. Right? So x is a vector, this is a vector. Now A plus alpha times x, I'm sorry, let's call it B. So alpha times B. A plus alpha times B is this vector, right? This is A plus alpha times B, right? And we notice that by adding some amount of B to A, the angle between them got closer, right? Which means you can expect A dot B to be A dot B plus alpha times A will be A transpose B plus alpha times A transpose A, and A transpose A is always positive, which means this will be greater than or equal to A transpose B, right? So if we have two vectors x and theta, or A and B, and we want the dot product between them to be bigger than what it currently is, one way to achieve it is to take one of the vectors and add a small amount of that vector to the other vector, right? Similarly, if the dot product between two vectors is bigger than what you would like it to be, right, you can take a small amount of one of the vectors and subtract it from the other vector, right? And here you just flip the sign, and A transpose A will always be positive, and so a negative value of A transpose A is going to be negative, and that will make the updated vector be smaller. So what does that mean with respect to our equation, update rule? What we say is, suppose y is 1 and the current value of h theta x is also 1, right? Which means according to the current parameter, we are correctly classifying ith example. Then this will be 0, and you don't modify theta at all, which means if you encounter an example that's already correctly classified, don't do anything, right? 1 minus 1 is 0. Similarly, if the current example has label 0 and you're outputting your h theta of x output 0, don't do anything. So if you encounter an example that's already being correctly classified by your half-trained model, don't do anything. However, if you encounter an example whose correct label is 1, but we are outputting 0, then this will be 1 minus 0 equals 1. So add some amount of x to theta. If you encounter an example whose true label is 1, but we are outputting 0, then add some amount of that vector to theta, right? Similarly, if the correct label is 0 and we are outputting 1, which means we are making a mistake, but a mistake in the other way, then 0 minus 1 is minus 1. So subtract some amount of that vector from the current parameter theta, right? If you start your theta vector to be 0, then what we see is the theta vector that we end up with is going to be some linear combination of sums of your x's. So everything that we have here, right, this is real valued, this is in RD, and this is RD, right? So all of this is just a scalar, and the the basis vectors that we are getting are basically just the examples themselves. Right? So what we are doing is adding small portions of our example to construct a theta, and we add them in such a way that if the current value of theta is misclassifying it, then we either add or subtract. So for example, let's see. So let's assume we encounter some x over here, which is labeled 0. Right? So this corresponds to y equals 0. Right? And theta transpose x is less than 0, or theta transpose x is going to be greater than 0 because the angle is less than 90 degrees, which means now we are going to add a small amount of this vector. Are we going to add? No, we're going to subtract, because the label is y equals 0. We're going to subtract some amount of this vector from theta. So what does that look like? So this is the vector. Take a small amount of that vector and subtract it from theta, and theta t plus 1 will, right, so this is theta t plus 1, and the decision boundary corresponding to theta t plus 1 will be this. Right? So the example which was classified as positive under the blue hypothesis, after performing their update rule, got correctly classified as negative under the updated hypothesis. Yes, question? So why is the separating hyperplane always orthogonal to theta? So theta is the current vector, right? And if you look over here, theta transpose x equal to 0 is like the decision boundary, because if theta transpose x is bigger than 0, it's considered positive, and if it's less than 0, it's considered negative. So you can think of theta transpose x equal to 0 as the separating boundary. And if theta is in a particular direction, the set of all x's that give you theta transpose x equal to 0 are all the set of all points that are kind of perpendicular to theta, right? Because if you take a dot product between two perpendicular vectors, the dot product is 0. Does that make sense? Yes, question? So in practice, you never use perceptron algorithm. Right? This algorithm is hardly used in practice. However, it is very useful to analyze this algorithm and to get some intuitions about how the update rule works, because this update rule pattern is going to come again and again. Right? Yeah. So this is the perceptron algorithm. There is theory which says if you're given a data set where the x's according to the classes can actually be separated, linearly separated, then this perceptron algorithm, which looks very simple, will actually find the separating hyperplane. Yes, question? So the question is, will we need to revisit a few examples again? Yeah. Yeah. So the question is, if it has 3 data points or if it has 1,000 data points, does it matter? Well, so the answer there is, if you have like a very small data set, then you may want to iterate over them a few times, right? But if you have a large enough data set, then generally just making one pass across the large data set should be sufficient. Yes, question?
Do you have an infinite amount of solutions, like of how you can handle that depending on your data?
Yeah. So the question is, aren't there an infinite number of correct solutions for theta for a given data set? The answer is yes. There are an infinite number of solutions, and this algorithm will find one solution, some solution. Yeah. Any other questions? Yes, question. Will the solution change according to the order of the examples? Yes, it can change according to the order of the examples. And that's fine, because we are generally interested in some solution that works. Yes, question? That's correct. We use, the question is, do we use one example at a time and not all of them? Yes. This, think of this as similar to SGD. Take one example, perform an update, pick another example, perform an update. Cool. So that's the perceptron algorithm. Now let's move on to logistic regression. Yes. So the question is, does the order matter? The theory of perceptrons tells you that if you have a large enough data set, go through it in any order, and you will find some separating, some valid solution. Yeah, so the order does not. Yeah, you'll get a different answer, but it'll still find some separate. Why don't we use this in practice? We don't use this in practice because there are many other algorithms that work better, and the perceptron algorithm, well, if you don't mind, ask the same question, remember it, ask the same question after logistic regression so that we can draw some comparisons. But the key takeaway from the perceptron algorithm is this idea that if you have two vectors and their dot product is smaller than what you would desire it to be, then take a small amount of one of the vectors and add it to the other, right? And that will make the dot product bigger. And similarly, if the dot product is larger than what you would like it to be, then take a small amount of one vector and subtract it from the other vector. How do we determine alpha? Just the way you determine alpha for gradient descent, right? Take a small amount. All right, logistic regression. So to start off with logistic regression, it would not be an understatement to say logistic regression is the workhorse of machine learning. It's probably one of the most commonly used algorithms in practice, in production. Right? Go to any company in Silicon Valley, the chances are if they have some kind of a classification problem, it's way more likely that they're using logistic regression compared to any other algorithm. And it's surprisingly effective, right? And it should probably be one of the first algorithms that you try for a classification problem that you're trying to solve, right? Always start with logistic regression. More likely than not, it's just going to work pretty well. So in logistic regression, the setting is very similar to the perceptron algorithm. We have x's in RD, y in 0, 1, right? And when yi equals 1, we call it a positive example. And when yi equal to 0, we call it a negative example. Right? And this is a description of the data. It does not, it is not a positive example and negative example does not mean the model is correctly classifying it or model is negatively classifying it. It's just the way we call the examples. If the label is +1, we call it a positive example. If the label is 0, we call it a negative example. Right? And the hypothesis for the logistic regression is going to look something like this. H theta of x is equal to g of theta transpose x, right? Where it is again similar to the perceptron's hypothesis, where h theta of x was equal to g of theta transpose x. The difference is g in this case is defined as follows. So g of z, where z is think of z as the value that you get after doing a theta transpose x. G of z is defined as 1 over 1 plus e to the minus z. Right? This function g of z, which has the form 1 over 1 plus e to the minus c, is also called the logistic function. Which is basically why this algorithm is called logistic regression. And it actually looks somewhat like the perceptron's g function. So g of z looks something like this. Supposing this is z, 0, this is 1. Right? So g of z looks something like this. Right? So g of z as, so the limit of g of z as z tends to minus infinity equals 0, and similarly the limit of g of z as z tends to plus infinity is, as z tends to plus infinity, g of z tends to 1, right? And this line over here is g of z equals 1 over 1 plus e to the minus z. Right? Now, if you compare this with the perceptron's z, in the case of perceptron, it was exactly equal to 0 until 0 and exactly equal to 1 when z was greater than 0. You can think of the logistic function as some kind of a soft version of the perceptron's version of g. Right? And now we define, just as in the case of linear regression, we define a likelihood function. Right? So we say p of y I equal to 1 given xi comma theta is equal to h theta of x, and similarly p of yi equals 0 given xi theta is equal to 1 minus h theta of x. What this means is, for any given x, any given example x, we take the theta vector that we have, do a dot product, we get some z value, run it through g of z, right? And it's going to give you a value between 0 and 1. And now the claim is, because it's a value between 0 and 1, we're going to pretend that it's a probability value, because probabilities are between 0 and 1. Right? So the probability of y equals 1 given x and theta is defined to be h theta of x. So supposing we have an x whose theta transpose x is plus 10. So z is going to be plus 10. G of z is going to be something very close to 1. Right? Similarly, if you have some example x whose theta transpose x is say minus 1, it's going to be here, and g of that is going to be a value that is close to 0. Right? And if you have an example x whose theta transpose x equals 0, g of 0 is 0.5. Right? So the interpretation here is that if the output of h theta x, or the output of h theta x will be closer to 1 if the model thinks it is a positive example, and it's going to be closer to 0 if the model thinks it's a negative example. Right? Because if it thinks it's a positive example, then you expect the model to have theta transpose x to be much bigger than 0. If it is if theta transpose x is much smaller than 0, then it would give it a very low probability. Right? And similarly, the probability that y equals 0 is always going to be the 1 minus of this function. Right? If this height is p of y equals 1 given x, and this height is p of y equals 0 given x. And because it's a binary setting, it must be the case that probability of y equals 1 plus probability of y equals 0 must equals 1. Right? Because we are talking about a binary setting. The sum of the two probabilities must always sum up to 1. Right? And the height of this function is basically the probability that the model assigns to that example that the label is 1. Right? So the correct way to think of logistic regression is that it is a probability machine. It's not actually a classifier. Right? It's a probability machine. For any given example, it outputs a probability. Right? And then it is up to us to choose some kind of a threshold. And a common threshold is 0.5. Right? It is up to us to choose some kind of a threshold and check whether the probability that was outputted was higher than that threshold or smaller than that threshold, and convert it into a classifier. Right? So logistic regression plus some chosen threshold will give you a classifier. Logistic regression by itself just outputs probabilities. Right? But it's common to just call logistic regression as a classification algorithm because we just assume that the threshold is 0.5. Right? So this is our hypothesis. Now, based on these two expressions, we're going to define the likelihood function. Right? So instead of writing a different expression for different values of y, we will instead write it in a compact way. P of y given x theta is equal to h theta of x to the power of y times 1 minus h theta of x to the power of 1 minus y. What's happening here? What's happening is if y is equal to 1, that is if y is equal to 1, the second term just becomes 0. 1 minus 1 is 0. Anything raised to the power 0 is times 1. So in the cases when y equals 1, it evaluates to this expression. In the cases when y equals to 0, it evaluates to this expression. Right? You think of this as how you would write if else in a programming language, and this is like the mathematical version of writing an if else. Right? So if y equals 1, it evaluates to this expression because this becomes 0. If y equals 0, then this entire thing is raised to the power 0 and you get this expression. So it's basically if else of this written in a compact way. Any questions? Yes. This is another way. Yes, the question is this another way to write an indicator function? Yes, this is another way to write an indicator function, but in a more compact way. Right? Yeah, think of it as an indicator function. Right? Yes, question? Okay, can you please repeat the question? So is there a version of this algorithm where the output of the algorithm is still a probability, but the label is? Sure. So if I understand the question, what you're saying is there a version of this algorithm where we take the predicted h theta of x, treat it as a probability, and sample y from it and act based on that? You can do that. You can do that. But it's far more common in practice where people choose some kind of a threshold and have a deterministic output. So the version of the algorithm that you described will behave randomly. right? And people don't like algorithms that behave randomly, right? They want their algorithms to, to be deterministic. So yeah, you can absolutely do. You can absolutely have a randomized classifier where you take the predicted probability and sample a y from that, and that's, theoretically that's perfectly fine, but in practice people just don't do that. Yeah, good question, right? So this is this is how we define p of y equals y given x, and in case of linear regression we came up with a p of y given x which had a Gaussian form, right? In case of logistic regression, this is actually a Bernoulli distribution. Think of this as a Bernoulli distribution where this is just p and this is the outcome. And given this, we can now define the likelihood function for your full data set. So L theta is going to be the product of I equals 1 to n and p of yi given xi theta, right? And we're able to break down our full data set into individual product of individual examples because of the IID assumption. Right? What do we do next? Just as before, we take the log likelihood, log L of theta, which is also commonly written as small l of theta, right? And this is going to be equal to the product changes into the sum, 1 to n, and so this term is equal to this, and we apply the logarithm to this term. Again, the product breaks into sum, this product broke into summation, and this product is also going to break into sum of two terms. It's going to be log of this term plus log of this term, right? Yes, question? Sir, can you please repeat the question? So y should be multiplied by p of x given. So what you're saying is, should we have p of y given x times p of x? Should we have this as well? So this will be p of y comma x. Okay?
So
Yeah, we'll parameterize by theta everywhere. So the question is, that's a very good question. Now, why are we considering our likelihood function to be p of y given x, and why is it not p of y comma x? Why aren't we maximizing the joint probability of x and y, and instead why are we maximizing just p of y given x, right? And what we will see later in the course is that for many algorithms we are going to maximize this as our objective, and those algorithms will be called generative algorithms or generative models, and the other algorithms which only limit themselves to the interest of y given x will be called discriminative algorithms. Right? For now, the intuition to have here is that when you deploy this model, somebody is going to give you x, right? You don't have a choice of deciding what x is. X gets thrown at you at production time, and you want to make a prediction on y given that x, right? And which is why we are mostly interested in p of y given x, making sure that we are able to making sure we're able to output a meaningful value of y when x is just given to you. Right? That's the general algorithm. But there are algorithms where we do with this. For now, let's just focus on discriminative algorithms this week. Right. Good question. Right. So back to the log likelihood. So the summation, so the log broke down this product into summation, and it's going to break down this product into a summation, right? And when we apply logarithm to the first half, it's going to be y I log h theta of xi plus 1 minus yi log 1 minus h theta of xi. Right? This is our log likelihood, which we want to maximize because we want to do maximum likelihood. Right? You can also optionally formulate a loss function for this, where you take the negative sign of this and you just think of that as a cost function, right? Which is, and then you want to minimize the cost function, which means, which is exactly the same as trying to maximize this. Right? And then we apply gradient descent. It is once you define a log likelihood of the parameters given the data, once you're able to write out it in this form, then it's just rote calculus. Just follow the same template, calculate the gradient, start your theta at some random initialization, and update it in some direction based on the gradient, right? And you do that over and over until you converge. It's the same algorithm once you define the likelihood function, right? So let's calculate the gradient. So in order to calculate the gradient, what we will do is, first we will observe that g of z, which is equal to 1 over 1 plus e to the minus z, and in practice, z will be theta transpose x. Right? The derivative of this is equal to, so you can look this up in the notes. I'm just going to skip the steps over here, or never mind, let's just do it. Right? So how do we calculate the derivative of this? So derivative of 1 over something is minus 1 over the same thing square, right, times the derivative of this, which in this case will be is times minus e to the minus z. Is that right? And this is equal to 1 over 1 plus e to the minus z times e to the z times 1 over 1 plus e to the minus z. Right? And over here you can add 1 and subtract 1 from the numerator, and this will be again 1 over 1 plus e to the minus z times 1 minus 1 plus e to the minus z over 1 plus e to the minus z. This is equal to 1 over minus z, and this will be just plus 1 minus 1, 1 plus z. So this will be 1 plus 1 minus 1 over 1 plus e to the minus z. Okay. And we see that this is actually equal to just g of z again times 1 minus g of z. Okay. So the derivative of the logistic function is equal to the logistic function times 1 minus the logistic function. Right. And using this, was there a question? No question. Right. So using this, let's calculate the gradient of the log likelihood. So L of theta is equal to, so let's just look at one example for now, with just one x and y, and for across all of them it's just summation over example. So I'm just going to use x and y for now. So L theta is y log h theta of x. H theta of x is just g of theta transpose x plus 1 minus y times log 1 minus g of theta transpose x, right? This is just the log likelihood written for one example, right? And now the gradient of this will be y times 1 over g of theta transpose x, because log of something is 1 over that, times g prime of theta transpose x times x plus 1 minus y times log of this is 1 over 1 minus g of theta transpose x times minus 1 times g prime of theta transpose x times x. Okay, just the chain rule. Any questions on this? Yes? How does taking the derivative of so this is based on the derivative with respect to theta of theta transpose x is equal to x. We reviewed this in class 2 or something, matrix calculus. Right? And this is y 1 over g of theta transpose x, and this is g of theta transpose x times 1 minus g of theta transpose x plus 1 minus y times 1 over 1 minus g of theta transpose x times minus 1 of, again g prime is g of theta transpose x times 1 minus g of theta transpose x times x. And this, these two cancel. Here, these two cancel. So what are we left with? We have y times 1 minus g of theta transpose x plus 1 minus y times minus 1 of g of theta transpose x. I think I forgot a times x here. So times x times x. Okay. So x and x are the only vector valued quantities. Everything else before that evaluates to a scalar. Right? Whenever you're doing matrix calculus, always keep tracking the dimensions. The left hand side, the gradient is a vector, and it's a vector because x is a vector and x is a vector. Everything else here evaluates to a scalar. Okay. Okay. And so this becomes y 1 minus g of theta transpose x minus comes here 1 minus y of g of theta transpose x, the whole thing times x, and this is just, so you have a y minus y g of theta transpose x minus g of theta transpose x, minus and minus, plus y g of theta transpose x, the whole thing times x, and these two cancel, and you're going to get the gradient to be equal to y minus g of theta transpose x is just h theta of x times x. So the gradient of theta of the likelihood with respect to theta is this, which means the update rule will look like theta equals theta plus alpha times the gradient, which is y minus h theta of x times x. Right? So we basically got the same update rule as the perceptron algorithm and the same update rule as linear regression, where the only thing that changes is the definition of h theta of x. Right? And again, this is not a coincidence. You will see why it's not a coincidence, but it looks very they look very similar. Any questions on this? Yes, question. Yeah. Good question. Was there a reason why we chose the logistic function? Could we have chosen something else, right? And the answer is the logistic function is a natural choice that you're going to see why it's a natural choice in the Friday lecture when we study generalized linear models. You can in general choose any other function instead of 1 over 1 plus e to the minus x. You can choose any other function that maps it between 0 and 1. You can define a likelihood function based on that version of g of theta, take the derivatives, and the update rule might look different, right? And by choosing the logistic function to be of this particular form, we get an update rule that looks similar to the other update rules, and we'll basically see the connection in the next lecture. Will we so the question is, will we deviate from linearity? And I'm intentionally not going to, go into more details. I know, and I'd suggest you to wait. Right. So this is logistic regression. Right. We got an update rule, and over here, if we want to do based on this update rule, we can perform gradient descent or stochastic gradient descent. If it is stochastic gradient descent, then we sample one example randomly, plug in the values of that example, update our theta. If it is a full gradient descent, then here there's going to be a summation across all your examples. Yes, any questions? Yes. So the question is here, are we going to look at all examples at once, or one by one like the perceptron? And that's going to depend on whether we choose to optimize this with gradient descent or stochastic gradient descent. Right? If we do gradient descent, then we are going to sum over all the examples. And if we choose to do stochastic gradient descent, then we choose one random example at a time, calculate this, this update rule and update your theta, and then pick another example, update your theta based on this update rule, and so on. Yes, the question is, are we looking at binary classification? Yes, for now we are just looking at binary classification, true or false. Right? And again, the thing to note here, if you want to compare it to perceptron, is that in the perceptron algorithm, assuming we start theta from 0, right, a vector of zeros, in the perceptron algorithm, we were basically adding or subtracting our examples, small fractions of our examples to theta to kind of make progress, right? And each time we were multiplying it by some amount alpha, and we were only performing this update if we got the example wrong in case of perceptron, right? But in logistic regression, what we see is that h theta of x is going to take some value between 0 and 1. It's going to look something like this, and it will never be exactly equal to 1 or 0, right? Which means in every step we will always take some amount of x, which is based on the difference between y and h theta of x. H theta of x is never exactly equal to 0 or 1. It will be some value between 0 and 1, right? And therefore you can think of this as like a soft version of the perceptron algorithm. Instead of deciding that we got this example correct and just discarding it, We're going to learn from every example, but by some amount, depending to the degree to which we got it right. Yes, question?
So given that data, because it's continuous, like how do you actually do prediction? So it's like given a validation example X and beta, when you calculate the logistic function, how do you actually determine output whether the predicted y is 1 or 0? Is it some sort of threshold?
Yeah, good question. So the question is, at test time, at validation time, we are given, we calculated theta during the training phase and we got a theta, and at test time we got a new example x. Now how do we classify it as 0 or 1, classify it as positive or negative? And the answer there is that first we go through the math, do theta transpose x, run it through the logistic function, and we're going to get a value between 0 and 1, right? And that's think of that as the probability that the model thinks the correct answer is 0 or 1. And then we're going to use, in practice, we're going to use some kind of a threshold. It's commonly 0.5. If the probability that was predicted was greater than that threshold, which is typically 0.5, we kind of think of that as a positive example. And as another student suggested some time ago, you could also take the probability and sample your y based on that probability. If the predicted output probability was like 0.99, then most of the times you're going to sample y equals 0, 1, y equal to 1, right? And that can be your prediction. In which case your model is like a random model. But if you have a threshold, then it's a deterministic model. Good question. Yes. Yeah. Yes. 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 So the question is, we can think of, in the case of perceptron, the resulting theta to be a linear combination of just the misclassified examples during the training phase, right? Whereas with logistic regression, it's going to be some linear combination of all your examples. Exactly. And the weights of that combination is going to depend on how correct or wrong we got each example during the training phase. Yes?
So if it's like more wrong, then the likelihood to be bigger.
Yeah. Yes. So the question is, during training phase, for when we encountered an example, if we got it like really wrong, we predicted a very low probability. When the correct answer was is equal to 1, then the difference is going to be big. Exactly. Right. So that's logistic regression, and you'll be implementing this in your homework. But in your homework, if I remember correctly, you'll be implementing it with Newton's method. So here is another optimization algorithm that you may use in place of gradient descent. Right? In the case of gradient descent, we just took the gradients and adjusted our theta values according to the direction in which the gradient pointed us to. Instead, there is another algorithm called Newton's method. Right? Newton's method. And think of this as alternative to gradient descent. Gradient descent or stochastic gradient descent. Think of this as an alternative to gradient descent. And the intuition for Newton's method is something like this. Right? So let's draw some pictures where so let's assume we are trying to minimize a function, minimize some kind of a loss function, right? And let's say your loss function looks like this. And similarly, for the same setting, here we are assuming a one-dimensional input, right? So the derivative, not the gradient, the derivative, let's call it L prime of theta. How would that look like? So until this point, the gradient is negative or the derivative is negative. So in this region, to the left of this minima, the function will probably look something like this. And then to the right of this point, the gradient is kind of positive, right? So maybe it kind of looks something like this. Right? Does that make sense? So this is our loss function, and this is the first derivative of our loss function. And what we want to do is find the point where the loss function is minimum, which means find the point where the derivative crosses 0. Right? Does that make sense? And there is this algorithm called Newton's method. So Newton's method is a way in which for any given function, some f of x, it's a way in which you can find those values of x for which f of x equals 0, right? And those values of input for which a function evaluates 0 are also called like the roots of the function, right? So Newton's method is a root finding method where for any given function f, it will find the input values at which the function evaluates to 0. And what we are going to do is apply Newton's method to the first derivative of our loss function, right? And the way Newton's method works is like this. Start with some random initialization, just like gradient descent, you start with some random initialization of your thetas. Let's call it this, let's call this theta of 1, the random initialization, right? And Newton's method will approximate the function by a linear function that is equal to the given function at that point. So maybe I'll use a different color. Right? So the black line is supposed to be a curvy line and the blue line is supposed to be a straight line, where the blue line is the linear approximation of the first derivative, right? And once you have a linear function, finding the root is very easy, right? And in Newton's method, what we do is approximate a function by the linear a linear function, and solve for the root of the linear function, and consider this to be your theta 1, right? And from this point, repeat the process, right? Calculate the construct a new approximation. So I'm going to mark iteration 2 with red color, and over here the linear approximation might look like this, and solve for the second approximation, and that's going to be theta 2, and so on. And once you get closer, Newton's method converges extremely fast to the true answer, right? What did we do in gradient descent? In gradient descent, we started over here, right? And the gradient pointed us in the rightward direction, and we took a small step here. And we saw that the gradient was still, and we took a small step here, and we kept taking small steps until we reached the minimum. In Newton's method, what we do is we look at the gradient function at the first derivative, at each step approximated by a linear function, and solve that linear function to be equal to 0. Right? and jump to that point. So say from theta 1 we did I get it wrong, so call this theta 0. From theta 0 we jump to theta 1, and from theta 1 we jump to theta 2, and what we see is that the rate at which the sequence of thetas converges to, say, the true theta star, or let's call this theta star as the true global minimum. The rate at which Newton's method converges is much, much faster than the rate at which regular gradient descent would converge. All right, and the Newton's method update rule looks like this. This question? So yeah, so the diagram was a little small. So let me draw a better version of the diagram. Right. So I'm going to draw. Let's assume this to be our. This is the first derivative, right? So start at some theta naught, right? So this is the derivative. There is a corresponding, true loss function, right? This is the derivative. This is not the loss function, right? So at this point, the function will, the function value is somewhere over here, right? It's a curved function. Instead, we approximate it by a linear function, right? Which means, and here I'm going to use a different color. So the blue line is the first linear approximation. Right? And this is going to be theta 1. Right? And similarly, this is L prime of theta 1, and construct yet another linear approximation at the new point. In the way and the place where the second one, this will be theta 2. Okay, does that make sense? At every point, construct a linear approximation, solve for the linear approximation, and the solution is the next location for our theta. That's where we move to. Yes, this question. Yes, so the question is, what happens if there's a non-convex function? I'm going to come to that. Right? Yeah, and the update rule for Newton's method is, supposing we call this f of theta. The update rule for Newton's method is theta of t plus 1 equals theta of t minus f of theta over f prime of theta. Right? This is the update rule for Newton's method. And now our f was the first derivative of our loss function. So if we plug in our loss function here, what we get is theta of t plus 1 equals theta of t minus L prime of theta over L double prime of theta. Does that make sense? Yeah, evaluate at theta t. Yes, question?
When you find new theta, does it do that for every point on the curve, or does it do like a step size where it comments in on the value?
So when we find the new theta, is there some kind of a step size here? Yeah. In practice, you will use a step size. I'm coming to that. And so this is Newton's method, but however, this was using scalar valued inputs. Right? In practice, however, our loss function has a vector valued input because we have theta is a vector, and so this was for in the scalar case a scalar theta. For vector theta, the update rule looks like this. Where right. So in the scalar case, we would divide the first derivative by the second derivative, but in a vector case, the first derivative is going to be a vector and the second derivative is going to be the Hessian matrix, right? And we cannot divide a vector by a matrix, right? That's not a meaningful operation. So instead what we have is this variant of Newton's method, which is called Newton-Raphson method, which is a vector version of Newton's method to for vector valued inputs, and H over here is the Hessian, and you invert the Hessian. That's like dividing the second, taking the reciprocal of the second derivative. So you invert the Hessian, multiply it by the gradient, and that's going to be the direction in which we're going to head. Right? And in practice, it is very common to have a learning rate here as well. Though in many cases you don't need an extra learning rate. So think of this, compare it to gradient descent. In gradient descent, it was pretty much the same except for having a Hessian, right? But in Newton's method, you multiplied by the multiplied by the Hessian as well, because essentially what's happening by multiplying it by the inverse Hessian is that you're trying to account for the curvature of the loss function. That's the intuition to have, right? In gradient descent, you're only looking at the direction of the steepest descent, but then the curvature of the function can be pretty unusual, and Newton's method kind of accounts for the second level curvature as well. And this algorithm generally works much faster in terms of the number of steps required to converge, but there's a catch. The catch is that calculating the gradient is O of d in terms of the time complexity, and that is all that we need for doing gradient descent. However, the Hessian is d by d, so you have O of d square for calculating the Hessian, and even further you need to invert the Hessian, so that's about order d cube, right? So if your d is high dimensional, then Newton's method, even though it requires a fewer number of steps, the cost of each step can be prohibitively high, right? And it is that trade-off that you need to do in terms of deciding whether you want to use gradient descent or Newton's method, right? Another point to note is that Newton's method is a root finding method, which means if your L prime of theta look like this, right? If your L prime of theta look like this, which means your cost function L of theta was like this, and then it went up, and then it came down again, right? Newton's method is going to find you one of the roots. Right? It could find either the root where the first derivative is going up, which means over here, or it could find a root where the first derivative was going down, which means over here. And it's going to depend on initialization. Did you initialize close to the first stationary point, or did you initialize close to the second stationary point? Newton's method is just going to take you to the nearest stationary point of that function. Right? Stationary point means a function where the gradient is 0. It could be a minima, it could be a maxima, it could be a saddle point. Right? Newton's method is going to just take you to the nearest stationary point, which also means that Newton's method, throw a function at it, it's going to take you to the nearest stationary point, and if it's a convex function, it's automatically minimizing it. If it is a concave function, it's automatically maximizing it. So it's kind of like plug and play. Right? You can even flip the sign of your function and throw it at Newton's method, and it's still going to recover the same point. Right? It's going to take you to the nearest stationary point. It could be a maxima or a minima. So flipping signs is not a problem. Right? So that's Newton's method. Yes, question? It's going to find the nearest stationary point. Right? If the nearest stationary point is the only stationary point, then it is, and it's the local minima, then it's the global minima. But if your function has lots of local minimas or lots of local maxima, it's just going to take you to the nearest stationary point. Right? And that's the reason Newton's method is most commonly used only with convex functions or concave functions. Whereas gradient descent does not have that limitation. Gradient descent will always take you down, down, and down. Right? If the nearest stationary point is a local maxima, gradient descent will not take you to it. The gradient descent will take you, only down. Whereas Newton method is just going to take you to the nearest stationary point. Yes, question. Yeah, so the for SGD, so Newton's method generally does not work well with SGD, and the reason is because if you take just a few examples, the Hessian may not be invertible, right? You need a lot of examples to make the Hessian invertible. So Newton's method generally does not work well with in an SGD kind of setting. Or maybe I misunderstood your question. No, it's not analogous to SGD. So the scalar version of Newton's method is analogous to having a model where you have only one parameter. That's when you can use this method. We take one sample at a time, not one parameter at a time. Okay. Yes, question. Yes. Yes. So gradient descent can be caught in a local minimum. That's right. Whereas with Newton's method, you get caught in the most nearby stationary point. It could be a maxima or a minima. Right? And it works really well when your function is convex, where you know that the nearest point is the global optimum. And that's when you want to use. Yes, question. You could end up in a maximum if you use with gradient descent. Was that the question? Yeah, if you started. So with gradient descent, if you so with gradient descent, if you have a function that has maximas and minimas, and you started exactly at the local maxima, then yes, gradient descent will not make progress because the gradient there is already 0. That's right. Okay, cool. So that's Newton's method. And in the last few remaining minutes, let's get some intuitions about functional analysis. So this is going to be for the last few minutes. What we're going to cover is, you can think of it as purely optional in the sense there are not going to be any questions on your homeworks or in your exam from the material for the rest of this lecture. But there are some the intuitions that you get from a functional analysis standpoint can be very useful for understanding many algorithms that we're going to cover later this quarter. Right. So what's functional analysis? So think of this as like a 5-minute overview of functional analysis. Functional analysis is like an advanced mathematical topic which you probably spend a year studying, but we're just going to look at some intuitions, right? So you can think of functional analysis as the study of functions. right? You think of it as like, a study of functions, but a more common or a more useful interpretation of functional analysis is think of it as linear algebra in infinite dimensions. Okay. So the last 10 minutes or 5 minutes that we're going to spend is basically, think of it as if you haven't seen this material before, think of it as some kind of a mental exercise to force yourself to think about vectors and functions in a different way, right? It's good to learn new things, but I think it's even better to learn new perspectives. And this perspective can be very useful when we study things like Gaussian processes and kernels and so forth, right? So so assume this is a vector space R3. Okay? Let's call it x1, x2, x3 as the axes, and you have some point V, right? And the claim that we're going to make is that functions and vectors are the same, right? Functions are, think of them as an infinite dimensional vector. And that might sound surprising initially because we think of vectors as something that's like straight and linear, right? And your function can be like sin x can be wiggly, right? So what's the connection there, right? So one way to see the connection is a vector. Think of this vector v as a function think of this vector v as a function defined over the domain, where the domain is right. So the index that we are going to the index of the of the space is going to serve as the input to the function. So supposing this function has let's see. So this function has, I'm going to call this v1, right? And this is v3, and similarly it has some, that's v2, right? Just the components of the vector, right? So you can think of writing this vector as v of 1 equals v1, v of 2 equals v2, v of 3 equals v3, where those are the components, right? Think of a vector as a function, right? Where the input that you're feeding is the axis, right? And the number of axes you have for the space is basically the domain of that function, of that vector, right? Now this vector you can also now visualize it as a function 1, 2, 3, right? So this vector, let's call it a blue vector. So v1 is some value, v2 is some value, v3 is some value, right? So think of it as a function whose domain is just 3 integers, and its values is real valued, right? Now if you look at a more common more x in R, and let's consider a function think of this as f of x equals x squared plus 1. Okay. Trying to draw the same analogy here, it's just that for this function we have an infinite number of inputs that we can pass. For these functions we had just 3 possible inputs. For this function we have an infinite number of inputs, right? And the value of the function at each point, so pretend this is one long vector, an infinitely long vector, where the value of each coordinate is the height of the function, right? So the value of the function is what you fill in that vector, right? So a vector in 3 dimension, we would write it as v1, v2, v3, and a function. Similarly, you can write this function as equal to f of x1, f of x2, right, and an infinite number of them, right. So a function can be explicitly written out with, by the values the function evaluates to at different points, and it looks very similar to a vector, right. It's just infinitely long, and this analogy is, you got to use some amount of imagination, because here, this works only for countably infinite kind of infinities. But imagine you can, you write it to every possible real value, right? It's like, an uncountably infinitely long vector, right? That's the kind of intuition you want to have. Now, just the way if you have a function defined over 3 elements, you can map it into a 3-dimensional space. In the same way, you can map this function in, an infinite dimensional space, right? So imagine you have an infinite number of axes, right? Imagine you have an infinite number of axes. I cannot draw it on the board, I'm sorry. And there is a point, let's call this f, such that x1, x2, x3, and there are, an infinite number of these, and the value of a function at a given axis, because each axis corresponds to one possible input. So the value of a function at a given input is the same as the coordinate of the vector at that axis, right? Which is the same analogy from here to here, right? The value of the function at a given input is basically the coordinate value of the vector along that axis, right? Just extend that to an infinite dimensions, which means now you can and having this functional space of functions being points in an infinite dimensional space will be super useful for some of the algorithms that we're going to study, right? And you can actually, to formalize this a little more, or to kind of strengthen your intuitions some more, let's kind of draw comparisons of different concepts. So on the one side, you're going to have finite case, infinite case. Right? In the finite case, you have a vector. I generally call it v. And in the infinite case, you have a function. Let's call it like f of t. Right? And in the finite case, you would have some kind of an index. Right? Think of like v1, v2, v3, the axes, which are like the indexes, and they are generally some kind of, say, 1 to d, for example, if you're in a d-dimensional space. And in case of the infinite case for functions, it's basically the domain over which the function is defined. Right? Over here it's like R. Right? And for a vector, you have components. Right? And in the infinite case, you have values of the function at different inputs. Right? Does it make sense? And vectors are generally represented with an explicit representation. Right? So you generally write v equals v1, v2, vd. Right? You just write out the actual values of the vector. But functions generally have some kind of a symbolic representation. Which means you have some kind of a shortcut where given the index what's the value, some kind of a rule that given the index what the value should be, right? You can just as well think of an explicit representation of function where you're just writing out all the values of the function at every possible input as one long vector, right? It's the same intuition you want to have. Right? And a few more things. So in vectors, you have a dot product. Right? Dot product where you can write the between two vectors u and v equals sum over I ui vi, right? And similarly with functions, you can actually take an inner product between two functions, and that would look like this, f comma g equal to integral of f of t g of t dt, and then this is perfectly valid inner product between two functions, right? It's just the extension of the inner product to an infinite dimensional setting, and in fact, this form you might be familiar. This if f is like a probability density function and g is like a random variable, your expectation of some g of x, where x is drawn according to some distribution p, is actually just the inner product between p and g. Right? And you have a matrix, right? Matrix A. The equivalent thing over here is some kind of a two-input function, right? Let's call it k of s comma t, where in a matrix A you have aij to be that the specific element of the ith row and jth column, but for in an infinite dimensional setting, just evaluate the function at the two given inputs, right? And so on, and you can each matrix is, you can think of it as a linear operator, which means you have linear operators on functional spaces as well, right? So for example, a of x, let's say y equals a of x, is a linear operation on a vector. Similarly, you can have a linear operation in functional space, and one such example is f prime equals d of f. You have a function f, and differentiation is a linear operator, right? And you get an output function, right? D is you can think of differentiation as one big infinite by infinite dimensional matrix, right? And and there are you can draw further analogies. For example, you have eigenvectors for a matrix A such that Ax equals lambda x. Similarly, for some kind of this is finite, this is infinite. Similarly, you can have eigenfunctions for some operator, right? So if f prime equal to d of f is equal to some lambda times f, then f is an eigenfunction and lambda is the eigenvalue. And for the differentiation, can you make a guess of what can be an eigenfunction for differentiation? Exactly. So say e to the kt, where t is the variable, is equal to k times e to the kt. Right? So you can think of the exponential as like an eigenfunction for the differentiation operator. Right? And the way we represent Ax, so if for example u equals Av, then we write ui is equal to summation over j aij vj, right? This is matrix multiplication, which means now the kind of equivalent in the g of s is equal to integral of, let's call it some k of s comma t f of t dt, where you see that so this is like a matrix multiplication, right? But it's just happening in infinite dimensional space, and these are also called integral transforms, right? And you might have come across many functions of this form already. For example, when k of s comma t is equal to e to the minus st, this becomes the Laplace transform, right? And if you have k of s comma t is equal to e to the minus ist, this becomes the Fourier transforms. Right? So you can think of Laplace transform as Fourier transforms as linear transformations. Instead of if it were a finite dimensional, it would be like a matrix multiplication. In an infinite dimensional, it's you run through some operator, just like multiplying through a matrix, and you get the index changes from t to s, which means from one axis the input changes to the other axis. Right? And the idea here is the big picture that you want to take away from all of this is that functions are points in an infinite dimensional space, right? And a lot of operations that you may already be familiar with all kinds of transformation, like the Laplace transform, Fourier transforms, are all just linear operations, including differentiation, are all linear operations on points in this infinite dimensional space. And these points, we call them functions, just the way we call vectors as points in a finite dimensional space. And this way of thinking, of thinking of functions, which we normally think of them as some kind of a curve along some axis, think of them as points in an infinite dimensional space, where the coordinate along each axis is the height of the function at that particular input, right? And this kind of mental dexterity of switching between these two views can be extremely useful when we study things like Gaussian processes or kernel methods or even gradient boosting, for later in the course, right? Anyway, so you're not going to ask any of these on your homeworks or exams, but it's just it's a new perspective where you start thinking of functions as just points, right? Not as curves or surfaces. Just think of them as some points that live in an infinite dimensional abstract space.